This is Pei Xiong. Today I would like to share our work, Textual-Visual Logic Challenge, Understanding and Reasoning in Text-to-Image Generation. In conventional image generation tasks, the model is required to output a 2D RGB image based on a given natural language input. However, when presented with a long, content-rich, and relation-heavy text prompt, current methodologies struggle to comprehend the complex input and its structural information, just like the Figure 1. The examples here in the Figure 2 indicate that the text input contains rich spatial relations. Additionally, there are contextual cues, often referencing the most recently added objects with it, rather than detailing its attributes. The results show that current methods can only generate the correct shapes and attributes individually. They often misalign these properties. For example, when given the prompt like generate a red cube, current methods may generate a blue cube and a red sphere separately, rather than a red cube. Additionally, these methods struggle to interpret and apply relational information from the input text, especially as the complexity of the instructions increases. Another challenge is from the evaluation matrix. We presented 3 results. The first one is correct, while the second and third one are incorrect. However, these three commonly used evaluation metrics do not accurately reflect the model's performance. This difference occurs because the input sentence introduces ambiguity, causing the image generation task to become an ill-posed problem without a unique solution. We now formally introduce a new task, logic-rich text-to-image generation, which differs from conventional text-to-image tasks by emphasizing semantic understanding limitations. Reasoning in text-to-image generation involves inferring relations and entities. Our focus is on spatial relations and entity inference, while the logic here denotes a structured reasoning process. To better evaluate understanding and reasoning in this text-to-image generation task, we collected a novel dataset, which has around 15,000 samples. Each sample includes a long, content-rich text prompt and its corresponding images. To assess the degree of the reasoning required, we have established 6 categories for the logic-rich text-to-image generation task, which are shown in the Figure 6. Figure 7 shows the distribution of each shape attribute composition. Our research focused on the balanced data with logic-rich text prompts. For the dataset like Microsoft Cocoa provide detailed annotation for basic training, they lack emphasis on the complex relational concepts and reasoning operations central to our task. Similarly, the SR2 datasets focus on the spatial relations, but overlooks logical operations and language diversity. These gaps highlight the need for a focus that captures a wider range of relational concepts and reasoning operations. The Table 1 here shows the related comparison in the prompt lens. The Table 2 over here shows the statistical data on reasoning concepts for better understanding the dataset's complexity. There are 2 concepts being mentioned. The first one is the account of a cross-sentence object referencing, and the second one is about the number of relations within the text prompts. Propose a generative adversarial network as a baseline model, emphasizing key aspects of the text-to-image generation task. It specializes in interpreting structured text information and aligning features across the unimodality and multimodality domains, which are shown in the Figure 8 over here. Due to the time limitation, I will briefly show the network architecture over here. It contains 3 modules. The first one is the relation understanding module, the second one is multimodality fusion module, and the third one is the negative pair discriminator. Here is the qualitative results. Here we show our results, the branches, and the 6 state of ours. We can see like the state of ours cannot handle complex relation information, and once the sentence gets longer, they will get lost in the cross-referencing. To evaluate the model performance, we also involve an extra evaluation matrix. It's similar to those used in the image manipulation task, measuring the results at the entity attribute level and relational similarity level. The relational similarity measures the similarity between 2 graphs and also consider the missing entity in the comparison, which is the recall. We conducted experiments for the overall results and application studies, and here are some of the results. Here are